Hello, good morning and good afternoon, everybody, wherever you are located. My name is Sara Pittonet. I am the coordinator of the Blue Cloud project, and I'm very happy to welcome you today to this workshop, part of the Ocean Best Practices series, the 8th edition. And today we're gonna give you an overview of Blue Cloud data-intensive workbenches for selected essential ocean variables. So I'll give you a brief introduction and context about the Blue Cloud project so that you can better than follow all my colleagues in the journey over this an hour and a half. Blue Cloud is an European funded initiative. It's supported by a program that is called Horizon Europe by the European Commission. It started in January 2023, but it relies on work that has been done at least since 2019. But actually, I can say that the collaboration is running since more years. Blue Cloud is building an open science platform for web-based science. And it builds on a work that has been developed and already since 2019, as I said. So since last year, we are actually evolving this open science platform into what we call a federated ecosystem to deliver fair and open science data, analytical services, and analytical tools. Instrumental for performing research for oceans in any and waters in any shape. The Blue Cloud project is responding to several policy directives, in particular some European ones that fall under the umbrella of the European Green Deal, but it also helps researchers responding to broader objectives such as the United Nations Sustainable Development Goals. And in particular, we're also supporting the movement towards what in Europe we call the EU destination herd, but in practical terms are efforts to develop digital twins, and in particular digital twins of the oceans. The Blue Cloud Consortium is broad. You can see here the 40 institutes that are working together toward this mission. They come from Europe, but they span data and services that go beyond frontiers and countries. As I mentioned, I come from a company that is named Trust IT Services. And together with me, the project is coordinated by two other institutes, the CNR, the Scientific National Research National Council in Italy, that acts as a scientific coordinator, and Maris, that you will meet today from the Netherlands, that acts as a technical coordinator. So this is the view that we have of our federated system. Blue Cloud, as I said, is developing open science collaborative research, which means that the data that we rely on are open science data, are open access data, and that the data products and the tools and the methodologies that we develop are also openly available and accessible. We believe in collaborative research, and so we're very glad to be with you today to show you a couple of those that we believe are best practices, and that's why we are here today out of our platform. As you see, there is a core element of the platform, which is the VIII, the virtual research environment, where a data discovery and access service is associated to bring into the platform data capabilities from different providers that you probably know already or that you will learn more about later. In the VIII, we build virtual laboratories, which are virtual spaces with actual experiments and models are developed within the realm, of course, of marine research, in particularly in aquaculture monitoring activities, for coastal observation services, maps of coast and ocean areas, but also to work on ocean variable products, fishery. We have a couple of fishery and one lab dedicated to marine environmental indicators. Last but not least, the consortium is working to develop workbenches as continued data flows of qualified and harmonized data for some essential ocean variables for physics, chemistry, and ecosystem. And actually, this is the first best practice that you'll learn today in this presentation, while the second is the data discovery and access service and the technologies behind it. So the workbenches that Blue Cloud is working on are conceived as efficient workflows for continuous data provision of essential ocean variables to allow researchers to access and use these data workflows as harmonized, validated, and qualified sources. Three of them have been developed, one on physical data, one on eutrophication data, and a third one on ecosystem data flows. Today, you'll receive a brief introduction about the approach of these workbenches by Marine Vernet from Ifremer in France. Then you'll listen to a presentation by Simona Simoncelli from ING-VU in Italy on the physical workbench as an example of the three that are being produced. And then you'll go a little bit deep dive into the mapping between vocabularies that is being done as part of the workbench for semantic harmonization, in particularly by Wen McNoyth from the National Oceanographic Centre in the UK. The second part of the course today is dedicated to the data discovery and access service, which is one of the two main components of the Blue Cloud technical framework. It aims at facilitating the discovery and retrieval of data sets by different Blue data infrastructures, those that you can see listed here, that made them accessible to the Blue Cloud Consortium. So you will learn more about the common interface that is being built and the shopping mechanisms that facilitate the retrieving of the data. In addition, you'll also learn about Beacon, which is the software systems behind the data discovery and access that allows indexing of specific data sets. So it works like a data lake. So can extract specific data based on users' requests, filtering them from millions of observational data files. And we will have today Dick Hart, from Maris in the Netherlands, the technical coordinator of Blue Cloud, that will introduce you to the data discovery and access service, and Robbie Kooiman from the same company that will present you the Beacon technology. And with that, I conclude and give the floor to my colleagues, and we'll start with Marine Vernet from Ifremer.
Just share my screen. Should see the slide full screen normally. Is that okay?
No, we can't see it. There's no sharing going on.
I can share them. Okay, now it's appearing. Yeah.
Okay.
Yeah.
Okay, perfect. So, welcome to everybody then. And I'm Marine Vernet. I work at EFREMER. I'm a data manager. EFREMER is a French research organization for exploration and exploitation of the sea. And I work in the Blue Cloud project in the coordination of the Workbenches package. So today I will briefly introduce you about the Workbench approach in the Blue Cloud project, the common objective, common expected outputs, and the challenges that are faced by those workbenches. So the essential ocean variables and essential biodiversity variables are of high importance for the analysis of the state of the environment, but currently data collection for EOV and EBV are based on large number of data packages of different types and different sources that are computationally intensive and that are processed by different experts using different methods, resulting in no interoperable data collection. So this is why the main idea of the workbenches in Blue Cloud is to design, build, and deploy on the Blue Cloud infrastructure and virtual research environments analytical pipelines in order to generate highly qualified and harmonized data collection for selected EOV and EBV using relevant input dataset from various marine or ocean data infrastructures. So the Blue Cloud project has created this great opportunity to gather together several data experts from different research communities and representing different blue data infrastructures and research performing organizations in order to work together on 3 different data-intensive workbenches. So the first one is the physical workbench, which aims at implementing a cloud-based workflow to generate harmonized, validated, and customizable EOV data collection for temperature and salinity variables on the Mediterranean Sea. And they will use as sources data from SeaDataNet, Copernicus Marine Service, Eurago, and the World Ocean Database from the NOAA. The second workbench focus on defining and implementing an efficient prediction workflow to merge multi-source dataset from the Copernicus Marine Service, EMODnet Chemistry, and the World Ocean Database in order to build highly qualified EOV datasets for eutrophication variables, so chlorophyll, nutrients, and oxygen on the Northeast Atlantic Sea. And those 2 workbenches aims at extending the spatial coverage from regional sea to global ocean by the end of the project. And third workbench is the ecosystem workbench, which aims at improving the availability, quality, and interoperability of large collection of plankton observations. To do so, they will develop or are developing an analytical workflow using machine learning technique to produce global intercomparable plankton biodiversity and biomasses maps and products with clear quality check protocols that are derived from habitat modeling best practices. And they will use different types of sources and that are the real-time plankton observation data from OBPS, GBIF, MATU, and Atlantico project, but also plankton observation from quantitative imaging through EcoTaxa, and also genomic method results from through the Magnify pipeline. So those EOV and EBV workbenches will have 2 main outputs. So first one is the harmonized, validated, highly consistent data sets per EOV and EBV that they will produce. So this data set will be duplicate-free and with additional quality control. So will cover a large, give a large temporal and spatial coverage And through the pipelines, I will be able to be regularly updated with the latest data released from the Blue Data infrastructure dataset that are used as inputs. And the second one are the automatic pipelines themselves that are developed by the workbenches that will be running on the Blue Cloud infrastructure, and that can be adjusted depending on user needs, meaning the user will be able to use pipeline and select the data input source he wants and select the parameters of interest he wants to perform his duplicate checks and quality control upon. And those automatic pipelines will be documented and associated with a quality control procedure, the quality control procedure that has been applied in order to be easily reused by anyone and also deployable on other infrastructures if needed. So these expected outputs are highly relevant to a wide range of users. For example, they are relevant for Blue Data infrastructures and data aggregators such as Copernicus Main Service or EMODnet that will use these harmonized and consistent data sets in their operational activities and to derive services. They're also really useful to data managers to perform, to use the pipelines and perform duplicate checks and quality control, and obtain more accurate and robust statistical ranges for their quality control. They are used to researchers and modelers in order to derive products, climatologies, or monitoring indicators. For example, the physical workbench outputs can be used to obtain up-to-date ocean heat content indicators. And both the products, but also the pipelines themselves that are powerful tools, are highly relevant to improve the numerical simulation of the digital twin of the ocean. So they reach a large range of users, and they are also beneficial to several stakeholders, such as the IPCC, regional sea conventions, and EU directives, EEA, but also educational sector, for example. But to produce these relevant outputs, so workbenches has to face some common challenges. So first one is that they are dealing with heterogeneous and incomplete data that are of different types and coming from different observation, obtained through different observation methods. For example, for the ecosystem workbench, they're working with plankton data from traditional counts, from quantitative imaging, from genomic methods. And those data are also have different metadata and are of different quality. So it's quite difficult to merge those different data sets to obtain an integrated, harmonized data set to use as input for the pipelines. So it raises also data access challenges to access the latest version of large dataset from those diverse and distributed Blue Data infrastructure repositories, and also to access a subset of interest in those different datasets for the user. There are obviously semantic harmonization that is really necessary here in order to merge those datasets and also to be able to handle efficiently duplicates. And finally, they face data computing challenges since the analytical pipelines are highly demanding in terms of IT resources and need to be run seamlessly regardless of the user possibilities at home. So in order to meet these challenges, the Blue Cloud project has adopted a collaborative, integrated approach to design and deploy the technical component together with the technical partners of the project and integrate them in the Blue Cloud infrastructure. So in order to meet the data access and harmonization challenges, the workbenches are working and relying on the discovery data access service, the beacon service, and the semantic analyzer service that will be presented in the next presentation. And they're also powered by the D4 Science infrastructure in Blue Cloud in order to meet the computing and processing challenges they face, so using the HPC resources, the cloud optimized services that are provided for this infrastructure. So here's an example of a workbench integration in the Blue Cloud infrastructure. So on the left, you can see that there are the Blue data infrastructure databases that are used as input sources for the pipeline, for the workbench. And on the right, the Blue Cloud virtual research environment and the eutrophication pipeline. It's a eutrophication pipeline that has been deployed in the virtual research environment. And we can see that there are different services that are needed to allow the user to perform duplicate detection, additional quality control, and data visualization on his variable and parameters of interest from the original data sets in order to produce those high quality products and derived climatologies. So it's really a complete environment, and I will not go into more detail because it will be presented by my colleagues a bit later. So yeah, as a take-home messages, I think that so we can say that Blue Cloud, EOV, and EBV workbenches are working towards producing some real outputs and assets for different types of users, so highly qualified and validated data collections for the different EOVs, data-intensive workbenches and tools that will relieve the burden of data discovery, access, and processing and qualification by simplifying the whole workflow. And best practices also, such as a common quality control procedure and duplicate handling methods that will be documented. I've added here the link towards the workbenches web pages, where you will also find the contacts of the workbenches partners and participants in order for you to contact them if you want any more information. So thank you for listening.
Thanks, Marine. And I'm happy to give now the floor to Simona for her introduction of the physics workbench. Feel free to ask any questions you might have for the speakers in the question and answer box. Simona, over to you.
Good morning, everybody. I am going to present the physics workbench, which is an example on how to speed up the workflow to derive key EOVs data products. So I will present the motivation, a little bit of background, and the design of what we of the workbench. So I will start with introducing that the societal benefit of science can be enhanced through a community effort to collect, manage, and share the data that usually are acquired with specific purposes. But we need to enable multiple stakeholders to reuse them many, many times and for other goals. We need to engage in this process multiple stakeholders along with the data lifecycle and the data value chain, because we need to continuously tailor data products requirements to the emerging societal needs. We need to identify and tackle the emerging gaps, and we need also to optimize the data flow. So let's take a look to the data value chain, which actually, let's say, starts with the implementation of a multi-discipline and multi-scale observing system, from which we gather data, and those data need to be ingested in Blue Data infrastructure, where we create and preserve consistent data sets. These data sets are then used, let's say, in a further step of the value chain to derive data products, so aggregated data sets, aggregated fields like climatologies, but also can be used to run some applications. Then these products can be used to derive indicators, assessment reports, and facilitate at the end the decision-making process, the prior planning of and policy, let's say, policy decision. So in the blue box, you see where the blue cloud context, where we want to use the data sets derived from the blue data available from the blue data infrastructure to feed workbenches in order to integrate data sets and be able to derive in virtual labs indicators for the assessment. These can also feed the digital twin of the ocean through also the contribution of additional data and products and models. So looking at the data lifecycle, if we start from the data provider, we gather data, and those data can be, let's say, can have a different processing levels, and in each processing level, metadata can be enriched, and also quality control procedure can be at different stages. Here I put the labels of FAIR and best practices because in this case, data management should follow the FAIR principles, and data gatherings should, at the beginning, implement best practices for the data assurance process. The data coming from different processing levels can be shared at different stages through data infrastructure where data are integrated, harmonized, and products are derived. Also, products should follow data management principles. So, focusing on the quality assurance and quality QC procedures, we see that along with the data lifecycle, we must implement several stages, QC and QA at different stages. So data from many actors are involved. It is important that the provenance and the quality information are preserved along with the products in order to assure transparency and traceability of the scientific knowledge generation process. So these QA and QC procedures must preserve integrity and must assure integrity and consistency and completeness of the data products that we are going to produce. So I want to give you an example from the SeaData Cloud project where we gather from the SeaDataNet network of National Oceanographic Data Center. What we did is to harvest many times all the data of temperature and salinity from the different data centers in Europe in order to aggregate files and parameters and perform QC at the regional level. What we do after QC is to prepare a list of anomalies that we want to send back to the data providers in order to continuously increase the quality of the database content. This process allows us to derive added value aggregated dataset, further validated, and from them we can derive the graded climatologies. In the SeaData Cloud project, we integrated data from different external Blue Data infrastructure, and what we learned from that example is that integrating data from SeaDataNet infrastructure with data from Copernicus and the World Ocean Database, we can increase the data coverage in time and space, and so derive, let's say, more accurate products. So starting from this, And also within the SeaData Cloud project, a pilot cloud environment has been designed and developed where that was actually used to replicate the database content to facilitate that access to the user and make it more efficient. But also this cloud environment was a first attempt of virtual research environments where the scientists could collaborate using services and tools to derive, again, products, subset of the products, or new and innovative data products. So let's go to the operational workflow. So the Blue Cloud Workbenches are should be designed to run operational workflows. So workflows are a series of processes that are necessary to complete a task, and its automation and the management process should increase the efficiency, optimize the results, and allow the replicability of the process and its monitoring. So the implementation is built on advanced services and FAIR principles. So if we start from a digital ecosystem of data infrastructure, and we use data and discovery access services and big data and cloud computing techniques on virtual research environments, we are able to derive added value data products. But in order to make it possible, we need to implement and use FAIR principle not only to data management, but to all the digital assets, so services, software that are developed and deployed on the virtual research environment. So from the generic workflow design, let's look at the ideal of the physical workbench. So starting from 4 different Blue Data infrastructure, Copernicus, SeaDataNet, EuroArgo, and World Ocean Database, we want to get the data products available, and we want to integrate those data through metadata harmonization, data integration, then duplicate removal, and additional QC. We want to implement this pipeline in a virtual research environment. We need for that a data lake service and a data discovery access service in order to facilitate the data access and speed up the data access from the cloud environment. And we need also interactive data navigation and visualization tool like the web ODV software in order to get our added value EOVs data set. A more technical design of the workbench is this, where I put all the ingredients. So we have on the left the Blue Data infrastructure that through Beacon, that is our data lake solution that will be described deeper later, we are gonna receive an integrated data set that we want to start looking and through Web ODV. And through Web ODV, we could actually do duplicate analysis and removal. We can also do additional QC, and we can validate the results before the release of the integrated data set. But the automatic pipeline in parallel can be run, and other tools will be deployed on the virtual research environment. Further validation. On one side, as I said, we have ODV, but we could have also DIVA-ND, which is a mapping tool that we use to compute climatologies. So this is, let's say, we're going to develop these and test these on the Mediterranean domain, but aim is to look at the global ocean. So focusing on the specific components, so Beacon is a high-performance data lake solution for fast big data harvesting and subsetting that enable efficient data consumption in the VRE. But in order to have metadata harmonization of these different data products from different data sources, we need to harmonize the metadata that are associated to the data. And for that, we have a semantic analyzer that provides a semantic harmonization that, coupled with Beacon, will give us the possibility to access harmonized data from different data sources. We are actually focusing on some metadata elements, platform instrument parameters and units, according to a Blue Cloud metadata model that we have defined in collaboration with all the partners of the project. So these are the essential metadata that we want to harmonize, starting from the complete metadata information that is available from each different data source. But what we want to do is to allow the user to be able to track back each observation, each data back to the original data source for provenance and traceability preservation. So getting farther on the pipeline, as I said, we have to tackle duplicates, and we want also to run additional QC to, let's say, guarantee consistency of the data, of the final data product. And we have on one side a WebODB that could be used to run the workflow, but is not, let's say, in an automatic way. What we want to do is also to deploy Clone Wars, that is a software developed by PocaPoc partner to detect and manage the duplicate, and the MinMax tool for QC, which is based on statistical methodologies. And we're going to have a real-time version of it and a delay mode version of it developed by PocaPoc or from OceanScope partners. Finally, as I said, the WebODB and Diva-ND will be used to verify the added value of the workbench workflow, of the added value of the workbench data set, and the efficiency of the workflow in deriving the data product. So to conclude, I would like to strengthen that fairness and best practices are actually the key drivers of this novelty, okay, of this operational workflow, because fair principles applied to the data and to the digital artifacts will allow interoperability of the solution, speeding up the knowledge generation. But best practices starting from the data gathering and going through the different quality assurance procedure along the data value chain are really needed to assure high quality results. Thank you.
Thank you very much, Simona. We had a couple of questions already, and I'd like to take them now since they relate to this part. So one was about the difference between Blue Cloud and Editor Infra. I've provided a short answer, but I don't know, Dick, if you want to also
Yeah, I just
provide.
also an answer,
Okay.
but
Yeah.
but it's quite complementary. I say what we do. Editor is DTO, and Editor Infra specifically is working on a data lake, which will be taking the data products from EMODnet and Copernicus, and then making them what we call HPC ready. And they have a term for this, ARCO data. While let's say the Blue Cloud, we are more building, let's say, an infrastructure where we bring together data, we bring together analytical solutions, and these are supported by cloud and computing resources. which allow us to build virtual labs and these workbenches. So it's much more an analytical framework, which is complementary to what's being done in DTO and EDITO. Because some of the analytical pipelines later might be adopted also in EDITO, say to run for in an operational sense.
Thanks.
So there's no overlap. There's really a very close cooperation, and there is a complementarity.
Thanks, Dick. And then a question for Simona. Do you also consider integration of data sources that do not come from science itself? Well, it's not just for Simona. But I will start with Simona. Yeah.
Not coming from science, I don't know what is. Well, let's say that we start from a demonstration. So the difference is that with the EDITO, where you can consume data produced by Copernicus and EMODnet, we wanted to integrate data from different sources. So let's say it is a little bit a step further in order to harmonize the data and maximize the number of data available. Of course, what can be done is from a user perspective in a later stage when this pipeline would be ready. I can foresee that a user might want to integrate his own data to this. But at this moment, we want to start with...
Simona, maybe I can add a little bit because you misunderstand the question, I think.
Okay, sorry.
Let's say what we have in the European landscape, we have some data aggregators and like SeaDataNet, like EOVs and others, and they are feeding into EMODnet and Copernicus. And in fact, in these pipelines, let's say we also work with industry data and from NGOs and citizen science more and more. So we have a very active activity, let's say, going on to work together with other groups in society that also bring in very useful data. The only thing is that the data must be validated and it must be fair. So that means there's a lot of education ongoing and also work ongoing, say, to help people understand better, let's say, what is fair, how they can transform the data to the right formats, and this way can ingest their data into these pipelines, which we are using. And Blue Cloud's effect is using those resources. So we are on top of this. And we make use of those blue data infrastructures that already are, let's say, connected to thousands of data originators, including companies, including NGOs, including citizen science. So I hope that makes it easier for you to understand. Okay.
Thanks, Dick. Okay, now I give the floor to Gwen Menkoif from the National Oceanographic Centre in the UK.
Thank you, Sarah. Could you confirm that you can see my slide all right?
Yes.
Yeah, okay, great, thanks. So, hello everybody. So I'm Gwen Menkoif from the National Oceanographic Centre, British Oceanographic Data Centre. I'm going to present our work on semantic harmonization and our approach using mapping between vocabularies. And this work is done in close collaboration with my colleague, Alexandra Kokinaki. And we manage at the British Oceanographic Data Centre, we manage a vocabulary server. So as was presented in the previous presentations, in the frame of the Blue Cloud project, we are dealing with a number of blue data infrastructure with heterogeneous data coming from those infrastructures, as well as other data sources. And those data sources are used by workbenches for compiling essential ocean and biodiversity data products. So in order to do this work, we need to carry out semantic harmonization between those heterogeneous data sources. So first identify the kind of vocabularies they're using and try to understand how this harmonization can be optimized. This harmonization will enable optimization of findability, discoverability, and also enable the workbenches to carry out analysis, comparison, duplicate checks, etc., as presented by Simona earlier. So we started with the Blue Cloud Common Data Metadata Profile, which was developed as part of the first phase of the Blue Cloud project. This is now being upgraded, but at the beginning of the project, this is all we had. So the different Blue Data infrastructure had produced metadata files that were formatted according to that profile. And in particular, we were interested in fields such as parameters, instrument, and platform. So a section of that metadata profile where the data providers would have provided descriptions of or terms related to those elements. And we were also interested in what was in the keyword section, where sometimes also we could find information that would be related to parameter, instrument, or platforms. So we reused a tool that was developed as part of the FAIRIS project, which was called the Semantic Analyzer, and we further developed it for the Blue Cloud project. So the Semantic Analyzer enabled us to objectively analyze metadata files, which would have been very difficult to do, even if they were very well structured. It's still very difficult to do across multiple data users and data providers. So the tool enables us to select metadata sources, and here I'm just highlighting some of the Blue Data infrastructures. And we can also feed or upload standalone files, list of terms that we want to analyze. And this is very useful in the first instance when we really try to understand the kind of vocabulary that's being used, what are they related to, and how they could be mapped. So the file sources, we can upload NetCDF, XML, or text files. And here I show an example of a text file, a list of terms that was uploaded recently in the Semantic Analyzer that comes from the Cora database. And it's just a mixed range, and I will show some of the outcome of that analysis. So those two methods of using the Semantic Analyzer both analyze incoming terminologies against a purpose-built knowledge base that sits behind the Semantic Analyzer, and that was built by ourselves using known vocabularies and known and trusted vocabularies. So here I show an analysis of a standalone list of terms, and at the bottom we've got like a summary report of the matching between the terms uploaded and what we have in the knowledge base. And it gives a summaries that can then be further explored in the upper section. And also there's possibility of choosing specific vocabularies that people might want to map against. And in this case, we can see from the exact match list, there are different vocabularies that have been, where terms have been found to have exact matches, like the CVOX device catalog, the SeaDataNet device categories, the WMO, the ICS platform codes. So it is possible to actually target specific vocabularies to narrow the search. It's also possible with the recent development to select which field we want to match and exclude deprecated terms as well. And finally, we also have a section that enable users to look at terms that have not been found as well and check them against other external semantic repositories. Finally, there's a possibility to export the file. So at this stage, this is a manual process. What has been sped up is really the comparison between the different semantic resources, but our intention is to develop API on the top of that. But once the analyzer is trained and we can trust the kind of mapping that comes out of the analyzer, but it's a development that will happen early next year. So this is the analysis of a full metadata record. So it shows it's possible to search for individual data records, but also to analyze an entire data infrastructure thanks to the GeoDAB report. And this has been extremely useful for the work with the workbenches and for analyzing the BDI use of terminologies. So as we said earlier, we focus on instruments, variable, and platforms. And the tool is designed to target those specific fields. And it performs exact matches or also proximity or wildcard matches. And again, for exploration, this is extremely useful. And here I'm going to show some example, like here it's an example of the match of a platform. So we used a data set from one of the BDI infrastructure. And there was a term in the metadata record, SVTARA, which could match potentially to 3 possible records in our database that were IC's platform codes. But only one of those was actually the good one. And this shows that by actually using more specific vocabularies and using URI, it is possible to avoid this kind of ambiguity. And once we've reached that stage, then we could have automated workflow for mapping different terms between different terminologies. So this is an example for instruments. So we had one exact match for this particular data set. And this exact match was this instrument, which is a sequencer of DNA. And we didn't have it in our oceanographic data collection, but we also ingested in the knowledge base, we ingested some vocabularies for instruments related to genomics or molecular biology. And there was an exact match for this instrument. So again, here, this is text match on preferred label, but if the URI is used, then there's no ambiguity about what the instrument is. And this is the record in its original semantic repository. And this is an example for parameters. So some of the files, the metadata files contain just text in the keywords that look like parameter, look like variable names. But again, we need to use that semantic search in order to identify what kind of parameter this is. And in this case, PCO2 in atmosphere does match to a P01 code, which is partial pressure of carbon dioxide in the atmosphere, which is much more precise than the original term, especially for the water body where it was just mentioned PCO2, but the actual P01 code is partial pressure of carbon dioxide in the water body. So there is way of actually improving the detail and decreasing the ambiguity of some of those labels. So the outcome of the high-level analysis at the infrastructure level exposed the need for improvement from a data source level, but also enabled us to identify commonly used semantic resources that we could then start investing time in building mappings against to avoid or to decrease the amount of work that the data sources would have to do. So as rules of harmonization, we are proposing, or we decided to have reference vocabularies for different level of granularity. So for example, for observation platforms, ideally, the platform needs to be identified at the instance level. And for this, we are using the IC's platform code, the C17, and that should be our reference. But it is also possible that instances are not available. And in that case, we go to the next level, which is a model level, using the BODC platform models, B76. And if this is not available, then we can go to the type, which is yet a coarser level of information, but often more frequently available and still very useful to have. And in this case, we're using the CVOX platform categories L06, as well as the Argo R23 vocabularies. So using those reference vocabularies, we are not imposing for them to be adopted, but we are mapping, we are actually creating mapping between what's come from the source data sets and those vocabularies to enable harmonization at the data lake level. And we're doing the same for instruments, using different type of vocabularies, and including a special vocabulary for XBTs, which is require more information than just a model level, because it contains also information about calibration of those XBTs. And then for the parameters, we selected the P01, the BODC parameter usage vocabulary, because it gives us a broad range of possibility of dealing with high granularity, low granularity parameters and combinations of different types of parameters as well. So it gives us maximum flexibility. And then for the unit, we're using the BODC unit vocabulary P06 and associated or mapped to the QUDT vocabulary, which is for NASA vocabulary for quantity, units, dimension, and types, which enables us to perform a conversion from unit to units. So this is a simple example of semantic harmonization using mappings. So we are looking at the data source, Copernicus, Marine Service, EMODnet, NOAA, and the label coming from their data resource are very different. The first one is C_water_temperature, the other one is water temp, and the other one is 1. Those URI or those labels or those codes can be mapped to either they come with their URI already, or they can be mapped to a URI using the semantic analyzer, or matched to their URI using the semantic analyzer. And we then build a mapping in the NERD vocab server to the P01 equivalent. And those mapping are then accessible from Beacon through Sparkle queries to create an harmonized data output. So with regards to, just a concluding slide, the Blue Cloud project's ambition and achievements are built on strong foundation of ocean best practices, as was mentioned earlier, and not least in the field of syntactic and semantic harmonization. We couldn't do what we're doing at the moment without all this work having taken place. And for over 50 years, work on semantic harmonization or harmonization of syntactic and semantic harmonization has taken place. And was started by the IOD network of National Oceanographic Data Center. But in Europe, it inspired the formation of this strong network of marine organizations bordering European seas, and those organizations agreeing to follow common standard and best practices to make their data assets more accessible and exchangeable. And using this legacy, as well as the work done in the other BDIs, and using semantic mappings, we are demonstrating that it is possible to harmonize across multiple infrastructures. And really, future best practice will require more systematic use of fair vocabularies, so findable, accessible, interoperable, and reusable vocabularies managed in semantic repositories, as well as UIs to enable more automated and more efficient workflows. Thank you very much.
Thanks a lot, Gwen. Very nice presentation and very interesting conclusions, both of you. Now we move to the second part. I'll leave the floor to Dix-Harp for the illustration of the Data Discovery and Access Service.
Mike, hi. Yeah, I want to tell you a little bit about what we call the federation of the Data Discovery and Access Servers. And the idea is that we have many leading repositories in the marine domain. And we would like to make it possible to have a common discovery and access to the data sets and the metadata. Let's see if is my slide working? No. Okay. So in the Blue Cloud, it's the data discovery and access service is one of the what we call key exploitable results. And we have, when we started the project, we started with the Blue Cloud pilot. And in that case, let's say we had the following blue data infrastructures on the left, which are quite, let's say, prominent research infrastructures and also EU initiatives like EMODnet and Copernicus Marine. And on the other side, let's say we have E infrastructures that are powering more or less the E infrastructure for the Blue Cloud. And what we built in the first project was what we call the first release of the data discovery and access. We brought together these, let's say the blue data infrastructure that you see on the top of the system. And we built a federated search to about, let's say, 10 million data sets, but we do it in a two-step approach, and I will explain it a little bit more. And also we include a shopping mechanism because the data comes from various, say multiple resources, and we are not copy pasting, let's say, all the data to a cloud, but we keep it where it is. But we have to bring it then together, let's say, in a basket, and therefore we also set up a so-called data broker mechanism. And but the data, you can use them as a user. So you can, let's say there's a user interface, but there's also an API, and you can also push it immediately through to the virtual research environment. So data sets can be ordered more or less by the virtual labs, and they can then make use of this mechanism. It's very, it's beneficial to users, of course, because they have only one interface to use, a common approach, let's say, to many resources, and that helps them to, they don't have to dig in all the different user interfaces. And also it's interesting for the managers of the blue data infrastructure because it helps them, let's say, to have a wider audience, let's say, to reach out to more users in a common way. And also we work, of course, together because what was explained before about this semantic harmonization, what we are in fact trying to achieve is that also that all the blue data infrastructure start using semantics in their output. And that so that the sources are, let's say, becoming more fair, by which the users and the systems can make a use of this, and that we do not have to do mapping between, let's say, only descriptive terms, but that we do mappings between URIs, and that's much more powerful and straightforward. So we have just an illustration of the different types of data that we have in the data discovery and access. Let's say it's from the different resources. It goes from chemistry, physics, geology, bathymetry, biology, genomics. What we do is we do it in a two-step approach. And first of all, we start with what we call identifying interesting data collections and products. And therefore, we use a few selection criteria, which are common to all the different blue data infrastructures. And this allows you, in fact, to find out, let's say, if what you're looking for is available in which BDIs that's available. And then second step is that you drill down in each of these BDIs using, again, a common interface. But then you go deeper with additional criteria, and then you go to the data level or the granular level. And this all works with machine-to-machine service. So there is no, it's all running by metadata and brokers and data broker services, which are all connected by different machine-to-machine services. And that's also an interesting challenge in the project, because over time it also helps, let's say, to improve the APIs and the web services that the blue data infrastructures are running to make them more fit for the purpose, and this way make them more fair as services. So you see this picture already. This is what we call the GeoDAP. GeoDAP is the metadata broker at the first level, at the collection level. It's a system that has been developed by our partner CNR in Italy, and it's very powerful and also being used already on a quite big scale. For instance, in the GEOS portal, it's the engine in the GEOS portal. And what it does is it can connect with different protocols, different web services to individual data repositories, then harvest, let's say, or the metadata from those and bring them into a common metadata profile, which you see on the left, and that you have a common output from this. So this way they are harmonizing, let's say, the heterogeneous landscape into a common metadata profile and bringing it together in a syntactic sense, as we just learned. At the second level, we work with what we call the data broker. And with the data broker, we have to deal with different services which are run at the individual blue data infrastructures. And you see several have dedicated APIs which might be, let's say, well documented and described. We also have Sparkle services. We have AirDAP. We have OTC CSW services. So there are many ways, let's say, to be able to communicate machine to machine. And we have to deal with all these different protocols and also with different profiles. Try to make them to the same point. This is an example how it works. So you have the interface, the user interface. There you see all the different BDIs. You start with some common approach by, let's say, the time and space and a free search. Then you get the collections that might fit your purpose. And those collections, they have also a lot of long boxes to on the map of the ocean. So they show you a little bit the area that they cover. Then you say, I want to go a little bit deeper. I want to choose one of them. So in this case, the Argo. And then you can add additional arguments, search criteria. You find then the so-called cycles, the data cycles from a specific Argo platform. And then you see, let's say, this as a result. These are the locations where the cycles are available. And the next step is that you can then retrieve the data associated with this. And that's being done by a cloud service that interacts with the BDIs with machine to machine. Let's say it retrieves the data sets and it puts them in a basket and then makes them available through the interface in a common way, combined with also data from other resources. Now we have the Blue Cloud 226 project, and there we are working on the next step in the process, in fact, upgrading the data discovery and access service. And one of the things is that we want to work more on harmonizing and expanding the functionality of the web services, because we found in the first round that we have to do a lot of, let's call it engineering or plumbing, let's say making things fit, and it could be done in a more fair way. Also, we'd like to expand the common metadata profile with extra fields, but also with semantic brokering, as was just explained, because we would like to harmonize the search and also the display by using this semantic mapping, semantic brokering. And therefore we make use of the semantic analyzer that was just explained by Gwen. Also, we are expanding the coverage. So we bring on board EMSO, CEOS, EOVnet Physics, and Elixir Magnify, which are 4 other blue data infrastructure with different types of data. And we are, in fact, we are connecting them and making the reach of the data discovery and access service wider. Now, this is the common metadata profile. So first of all, these are the fields that we want to support by extra metadata elements and also by semantic analyzer elements. And that also includes the organizations, because organizations, of course, play a very important role in many aspects. Let's say they collect data, they manage data, they distribute data. And we have also for this, as part of SeaDataNet, we have a common let's say vocabulary, which is called EDMO, European Directory of Marine Organizations. But over time, this has been also picked up by other organizations, also in US and in Australia and Canada. It has become more and more an international vocabulary. And this way you're able, let's say, to give a code to every organization, which helps you to bring everything together, because an organization is linked to data, is linked to projects, is linked to cruises. So you can more or less in a linked data model, you can play with this. And that's what we in practice do. Now this is then an example. Let's say that we add URIs. So we promote adding URIs. And as Gwen explained, we are doing the semantic analysis, let's say, to get to these URIs. But preferably, of course, we pick them up immediately from the source. And that's part of the process that we are dealing with the blue data infrastructures, that we try to educate them to make more use of the URIs in their expressions, in their XML and other output that they are sending by the machine-to-machine exchanges. And this is, let's say, to show you a little bit how the broker works, but you understand now after all the discussions and explanations. So what we do in the further development right now is that we ask every BDI to publish to make available, to publish, let's say, their semantic expressions and tell us if they are using vocabulary, and then make those expressions available. We also use what's already there in place. We are using that to analyze and to do the semantic brokerage, so to bring it together, to harmonize it. And we are, let's say, working together with several BDIs to add flavor or add fairness to their output by adopting vocabularies, and we recommend them to use the SeaDataNet standards, which are widely available and widely used, and also in EMODnet and in Copernicus, and also in the DTO it will be used, to adopt those, let's say, as if if they're not already using a vocabulary. And finally, what will happen is from this is that through this process, the BDIs will become more fair. They will their web services will be more fair, but also their output will be more fair. And that means that they can be more easily being federated, but they also, their own services will improve this way. And also, let's say they will be more fit for things like the analytical workflows, like the workbenches, which make use of these mappings, and for which we are doing now a lot of extra effort, which in the future will not be necessary anymore, because there is a much more harmonized output than immediately, which is run by machine to machine and analytical machines, which do apply the mapping. And that's a little bit what I want to tell you. Let's say if you look at the results of this work, we hope to release the new version of the Data Discovery Access by early next year. While the present one is already available, if you go to the Blue Cloud website, you can try it out. Get on let's say, registration as a user, and then try it out and see how easy it is, because it really works very nicely and gives you access to a wealth of data which is already out there. Thank you. So I hope
Thanks.
I catch up a little bit at a time. Robin has 15 minutes left. That's okay.
Yeah.
That's good.
Let's give the floor to Robin, and if you have
Okay.
questions, use the question and answer tab.
Hello. Sorry. Hello, everyone. Can you all see my screen?
We see you're not on projection mode.
Oh, wait. Now it should be better. Hi, everyone. I'm Robin. I'm here to talk a little bit about Beacon, which is a high-performance data lake and processing platform designed for subsetting access to large quantities of climate data. A little bit about the origin of Beacon is that a couple of years ago, we had the issue where we had millions of these data sets, millions upon millions of these NetCDF files. And we wanted to provide subsetting access to these millions of NetCDF files. So instead of when you go to, for example, when you go to SeaDataNet, you order a certain area, what you use to get back is a bunch of these NetCDF data sets. They could be tens of thousands of these NetCDF data sets. And once you got them back, you also had information that were not relevant to your query. And you had to filter these out for every data set, and you had to do a bunch of manual work to clean up your data, basically. And with Beacon, you can essentially get around this work by querying through Beacon. And Beacon is a data lake tool that allows you direct subsetting access on top of existing data collections. So an example is, I would like to have all the temperature data in the North Sea between 2010 and 2020 in degrees Celsius at a depth between 0 and 50 meters. And as a response from Beacon, you get one NetCDF file containing exactly this data, all harmonized, and it's directly usable in your notebook or on the web or anywhere you would like to use it. And it's all happening on the fly. And it does it with incredible performance. And within a couple of seconds, you'll be able to work with your data containing millions of these records from these thousands of data sets within SeaDataNet, for example. So some of the use case for Beacon is scientific research. It can generate and analyze really large data sets. It can provide access to large geospatial data sets, and also access to, for example, data streams from IoT systems or sensor networks that can directly feed into Beacon, and then users will be able to directly query Beacon and get access to the data sets provided by these sensor networks, for example. So what's Beacon, or a little bit about Beacon in a nutshell, is Beacon is written in Rust and C. It's a high-performance data lake. It runs on Linux, Windows, macOS, and through Docker containers. It basically consists of a REST API, then some core libraries that provide these high-performance capabilities. It allows for real-time subsetting and also data harmonization, where it provides one single output file, and also dynamic chunking, very similar to ZAR, a little bit more powerful to in-situ observations. Beacon then can produce various output formats such as NetCDF, CSV, JSON, GeoJSON, Apache Arrow, IPC, and Parquet, and also WebODV ASCII. And with Beacon can handle any type of multidimensional data. For example, it can handle time series, cruises, gridded, whether it's one-dimensional, two-dimensional, three-dimensional, four-dimensional. For Beacon, it doesn't matter. You can just import them into Beacon, and Beacon will understand how to format this data correctly so users can query upon it. Beacon allows you to have powerful query capabilities. You can filter on ranges, you can filter using polygons, you can filter using metadata, you can build union and aggregation queries. And also you can run federated queries across multiple Beacon instances, and then even harmonize across these instances together into one single harmonized output file. So a little bit about the performance of Beacon. We have a small benchmark for SeaDataNet, where you have around 2.5 million datasets, over 4 billion data points, all inserted into one single Beacon node. Then you run the query where the latitude is between -8 and 12. The latitude is from between 50 and 61. The depth between 0 and 50, and the time between 2010 and 2012. And I would like to have all of the different SeaDataNet temperature parameters aggregated together into one P01, into one column. And then want all the different units also harmonized to degrees Celsius. And the result file is contains 12 million data points, and Beacon just serves it out within, well, in the graph you can see takes around 2.5 seconds for you to get your result back to be used in your notebook, and that contains millions of these data points directly usable for scientists and users to work upon. Next to that, Beacon is also very efficient. So Beacon doesn't use a lot of RAM. It can hold millions of data sets and hundreds of gigabytes of data. For example, when you look at the Argo collection that we've loaded into Beacon, it contains around 600 gigabytes of NetCF data, around 3.3 million NetCF data sets. And Beacon just used around 600 megabytes of RAM and only 50 gigabytes of disk space to host the entire Argo float collection, where you can quickly query upon. And Beacon has also been made to be extremely easy to use for others when you're hosting it. So it's really very easy to start importing your datasets into Beacon. As I said before, Beacon is available through, or you can use Beacon via REST API. So to import datasets into Beacon, you query you create a post request to the Beacon API, where you tell it what kind of format you're importing, the path to the file you're importing, and then what kind of identifier you would like to give that NetCF file or other CSV files, for example. And that's all you need to do. You don't need to define what its dimensions are or what kind of columns you would like to import. It just works. You can just import the NetCF file and it will work. Querying Beacon is also quite simple. What you do is you give it the names of the columns you would like to query. You give it an alias in the output or an alias for the output, and then you can provide some filters. And then at the bottom, you can set the output format that you would like. So you can select a NetCF, or you can select WebODV, or you can select Parquet or Arrow, and there's much more to do. You can really play around with it and see how much data you get back. We've also made some notebooks available for everybody who would like to try it out through the Blue Cloud, which is available at the link in the slide. And we also have documentation, of course, available for using the Beacon API, whether it's through Swagger or the actual documentation on the website that's hosted on GitHub. A little bit about the status of Beacon, what's currently in public beta. You can play around with it, you can sign up, then you get you'll be signed up for the Beacon technical preview, where you eventually get access to trying out Beacon, playing around with it. And then you can set up your own Beacon instance and see if it works for you with your data. And you can build notebooks upon it. And within the Blue Cloud, we've made various instances of Beacon available on top of existing collections, such as the EuroArgo collection, the Core Profile data, Core Time Series data, EMODnet Chemistry data, the World Ocean Database, SeaDataNet TNS collection, and SeaDataNet Incremental, and also CMEMS biochemistry data we've made available as individual Beacon instances where users can query upon. And what Beacon likes to do is then use it, of course, in your notebook if you'd like. And these kind of examples that you see here is what you can do in your notebook within a couple of seconds, just querying through WOD, for example, here for a year's worth of data. for the whole world. And Beacon just gives you, within a couple of seconds, gives you a NetCDF file or another format. And you can instantly use your notebook to display it, right there. And it happens within seconds. And this is the example for Core RTS. Beacon is really performant, so even when you're working upon billions of these data points, within seconds you have a result file containing millions of temperature data points that you can display on the web or in your notebook, and Beacon does it all for you. And of course, this also works on top of SeaDataNet and Argo, so you can do it all on the fly. And we've built a WMS where you can see it actually in your browser, how it's working and displaying data on the map. And of course, you can also build some graphs about around your data. So here's an example where we plot all of the temperature or the North Sea temperature data between 1950 and 2020 for the WOD, for Cora, and for Argo. And this all happens within just a couple of seconds in your notebook, and you can run this. This notebook is available at the GitHub. So if you'd like to play around with it, feel free. And also to add on a little bit, we already talked a little bit about the semantic harmonization that we're trying to do together with Gwen and what she talked about in her presentation, where we harmonize the various monolithic beacon instances, these individual beacons on top of these collections, where we merge them together into one harmonized beacon instances, or beacon instance where users then can query upon a harmonized version of beacon where all the metadata is harmonized, units are harmonized, parameters are harmonized. And then users can play around with it how they would like to further harmonize their data using methods within Beacon. And this allows you to, of course, then combine results from for the Argo collection, from SeaDataNet, from WOD, from Cora, everything else that we have instance for, you can then combine and harmonize together in your output. So a little bit about the next steps for Beacon is that we're working towards a 1.0.0 release, probably around the end of this year, which will make it possible to set up your own Beacon node through a Docker container where you can import your datasets and just be ready for querying. We're also looking to build more upon a high-performance data distribution network through the federated query possibilities of Beacon. We'd like to also extend more query possibilities through more functionality where you can convert more units. You can do more convoluted calculations upon your data within Beacon. And would also like to explore the support for cloud. And of course, we're trying to make Beacon community-driven, where users can provide plugins written in Python that can inject itself into the Beacon code base, where you can then run extensions for your Python scripts upon the Beacon data frames. So if you'd like to get more or learn more about Beacon, feel free to contact us. I think that's it for me.
Maybe addition is that let's say the Beacon instances are now being deployed on the Blue Cloud, on the virtual research environment. That means that within, I hope next week, let's say they are available for all Blue Cloud users, and everybody can become a Blue Cloud user very easily by registration. And then you can use those monolithic instances for these different leading Blue data infrastructure. You can try them out and see how it works for you. And secondly, let's say we are working on this merger. Let's say these mergers, of course, are aimed right now for the workbenches because they have specific combinations of resources, and that will be together with this semantic analyzer. Let's say making a harmonized output, or you can say input for the further work of the workbenches. That's our aim, and that's also a very good test case because the researchers of the workbench, they will work with it and they give a lot of feedback, of course, to improve what we are doing right now. And this way, it will be a very interesting, I would say, offer for and also facility for many other applications to come in the near future.
Thanks, Dick. Thanks, Robin. We have a couple of questions that I see are from all our speakers. One was with the redundancy issues in the data provision, and the other one in the different quality of data sets related to the instrumentations that they have been guarded with.
We can answer the first one because let's say what we do is when we are merging these beacon instances, we have a so-called common metadata profile, which has the priority fields, and that has been defined, let's say, by the workbench group. And and in fact, we are mapping, let's say, the information, the metadata information from the different resources to this common profile. And that's in several cases, it's very straightforward. The only thing, of course, they don't use the same semantics, but finding an instrument, finding a project, these kind of things is not so difficult. And let's say, and then we work on this together with the semantic analyzer, let's say, to be able to make also the semantic harmonization possible, to have a more harmonized output. For the second one, I give the word to Simona, because she can deal a little bit better, let's say, how they deal with the quality differences that might be available.
Well, actually, what we are doing is to rely on the quality control and the quality flags that are coming from the different Blue Data infrastructure. Each data has been already qualified, and we start and we add an additional layer of quality and validation, which is in this graph. So, and in the case of duplicates and also additional quality control, what we are doing is to feed back to the Blue Data infrastructure with a list of potential duplicates and a list of anomalies. So the idea is, of course, thanks to the harmonization of the metadata, to first identify the principal kind of duplicates and then decide through rules what to do. I mean, how to flag and how to manage, let's say, in the further steps of the workflow, the duplicates. And the idea is to provide to the user the possibility to select which kind of duplicates to remove or to bring forward in the analysis, as also the quality level that might depends on the application that the user wants to add. So the idea of the workbench is to provide a workflow with different options from a user perspective in order to allow different solution for the application needed.
Thanks a lot. I hope we were clear enough. Thanks for your questions and for following us. I think we're done for today. So thanks a lot to our speakers and to the OBPS organizers. And for all of you attended, you can find, all information on the Blue Cloud website, including way to access the VIII and to get in touch with us. So we wish you all a pleasant rest of the day. Thank you all.
Thank you.
Thank you. Bye.
Thank
Bye,
you.
everybody.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.